All right. Well, thanks for joining me for this training from Bell Performance on the subject of cetane number improvers, their uses, and their benefits. I'm Eric Bjornstad. I'm the Technical Information Director here at Bell. So thanks for joining me. And we're going to talk about a few things, interesting things with respect to these chemical cetane improvers that you can add to fuel. We're going to talk about how they're used. We are going to talk about why they are needed, and we're going to talk about the specific practical benefits that they can give. And cetane improvers are a different breed than some of the other diesel additives out there because they have the chemistry of the whole issue of cetane is a little more defined than some of the other chemistries. And what I mean by that is the effect that they have is it's faster, it's more noticeable, and it's more documentable in a shorter period of time than some of the other still legitimate fuel additives and fuel chemical treatments like certain kinds of detergents and lubricity improvers. So it's very much to our benefit to be familiar with what cetane number improvers, or what they call CNIs, what these do, how they do it, and what you can expect when you use one of them. So in order to understand these, we have to understand a few different terms. You can read these definitions on the screen. I'll just run through them. First thing, we're going to talk about this issue of compression ignition, which is basically how a diesel engine operates. A diesel engine does not have a spark plug, so it doesn't have a spark ignition source to ignite the fuel, so it relies on compression ignition, where when you compress a volume of gas, if all of the things are being equal, then according to ideal gas law, the temperature of that gas will increase. And within a diesel engine, you'll have a situation where the temperature will be higher than the ignition temperature of the fuel or the gas, and when that happens, the gas will ignite. So that is basically how a diesel engine works. Now, when we talk about ignition quality, when we say that a diesel fuel has good ignition quality or bad ignition quality, well, that's just a basic reference to how easily that fuel ignites versus not as easily. All right, cetane. Cetane itself is used as a term to designate some kind of measurement of that ignition quality of the fuel. And cetane is based upon measuring the ignition delay. Now, what is ignition delay? Well, ignition delay is part of the combustion phase. We will see this here in a couple of slides. What happens when you inject fuel, diesel fuel, into a combustion chamber where there's air present, it does not immediately ignite. There's a delay. There's a time interval between when it is injected and then when it actually ignites. And what we find is that whether that delay is long or short can affect what happens inside of that cylinder and combustion chamber, and it can then affect how the engine operates off that fuel. All right, so the last bullet, we say that the ASTM defines cetane number. Cetane number is defined as it's an index measurement of the ignition performance of that diesel fuel, and it's calculated by comparing it to a couple of different reference fuels, putting it into a formula, and you get an index that is, or an index rating, which is referred to as the cetane number or the cetane rating of that fuel. ASTM stands for the American Society for Testing and Materials, and they are the group that basically works with government and works with industry leaders and people within given industries to come up with ways to measure things that are meaningful to the people that need to know them. So if you see any of our other trainings, this will not be the last time that you hear about the ASTM. Okay, so what we have here is we have 4 stages of the 4-stroke diesel combustion process. So in order to understand what's going on here, it's useful for us to be able to know exactly what happens here. So these the four strokes of combustion are air intake, compression, expansion, and exhaust. And what we have here are cutaways, side cutaways of what a combustion chamber looks like. You have here is the cylinder here. Inside the cylinder, of course, is a piston head with the crown. It's being driven by a shaft which spins on the crankshaft, and of course the crankshaft spins like this, and as it spins, it drives the piston up and down, and up here you have a place for air to come in with a valve that allows the air to come in versus sealing off the shaft or sealing off the chamber, whether it's open or closed. And of course, another valve on the other side that opens and closes to allow exhaust gas to exit. And then lastly, of course, we have the fuel injector here. So the first stroke is the air intake stroke. Now what's happening is that this is spinning. The piston is on its way up. This valve opens, draws air in, so air comes in here, and you have air inside of this volume of the combustion chamber. As the piston continues to move up, you can see that it's now a little bit higher than it was here. Now the injector injects fuel into that combustion chamber. The fuel mixes with the air, and it is now being compressed because the piston is moving up and it is lessening the volume of this chamber. So the gas in here is now being compressed. And at some point, it's going to increase in temperature, and once that temperature rises above the ignition temperature of that mixture, that fuel is going to ignite. When it ignites, it's going to explode, and there's going to be explosive pressure waves that are generated. And when that happens, it's going to, there's going to be expansion within that chamber, and it's going to drive that piston back down. And when it drives back down, now this gas is no longer being compressed. And so what you'll have, and of course, not only is it not being compressed, but because it's driving the piston back down, of course, that is what is going to make the engine able to do what it does. And then the last part is the exhaust. The gas is now spent, and so this valve opens, and the spent exhaust gas mixture goes out here, and then it gets ready to start all over again. Okay, so in order to understand what's happening inside of the cylinder, inside of the combustion chamber, when the fuel ignites, it's useful to look at a simple diagram of cylinder pressure. Okay, so what we have here is we have a graph of cylinder pressure on the y-axis as compared to time. Now, we have a bunch of lines here. We're going to explain what all you're looking at here. Now, remember that during this process, the cylinder head or the piston is going up and down. Now, as the piston goes up, remember, it compresses whatever air is inside of that combustion chamber, inside of that volume above it. Now, let's assume that we're not going to be injecting any fuel in there. Let's just assume that the cylinder, the piston is just moving up and down. What's going to happen is that, time is lapsing here, the cylinder is going up, and it's compressing that air in there a little bit. So you can see that the pressure inside is actually, it's rising. And it's going to rise until this point where the cylinder reaches what they call top dead center. Basically, it reaches the top of its stroke. So the air volume, the gas volume in there, the volume of space is compressed to the maximum it's going to be compressed. And therefore, it stands to reason that the pressure inside of that compressed space is going to be at its peak here. Now the cylinder moves back down, piston moves back down, it's no longer being compressed, so the pressure is going to go back down. It's going to go back down gradually, and that's basically what it looks like. You have a nice smooth curve like here that peaks here and then goes back down nice and smooth. It's like a little flat bell curve basically. Now, let's actually inject some fuel in there. All right, so piston's moving up. At this point here is when we're going to inject the fuel. Now remember, we said that there was an ignition delay. So there's going to be a delay, a short period of time between when the fuel is injected here and when it decides to ignite. And what we can see is that depending on if that delay is long or short, that affects, changes how the pressure rises and builds up inside of that combustion chamber after the fuel has ignited. So the first thing to do, let's look at a longer ignition delay. That is what we're going to look at from here to here. This is a longer ignition delay. So fuel gets injected here. Remember, piston is still going up, but the fuel has not ignited yet. And that's going to be illustrated by this black line here. Now, here's when the delay stops, and boom, the fuel ignites. And so what you then happen is you have a very steep and pretty great rise in pressure. In fact, the pressure suddenly spikes and goes up, 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 up. Now here, remember, here is where top dead center is. So the piston is at its top here, but the pressure is still increasing. And it is that increase in pressure, the fact the pressure is still increasing, that's going to drive that piston back down. So the piston basically stops and goes back down, again turning the crankshaft, turning the wheels. In the meantime, the pressure is still rising. It's going to rise up to about here. So it tops out here, and then it falls. There's no more, it's not exploding anymore, and so the pressure drops off just about as dramatically as it rose. Okay, and that's a graph of what happens to the pressure inside of that cylinder. But let's inject fuel that's of a higher cetane, a better quality. And a higher cetane fuel will, in principle, it will have a shorter ignition delay. So instead of taking from here to ignite, it's only going to take from here to here. So fuel's injected, it ignites here, and the pressure for this scenario is portrayed by the red line. So what they have found is that, of course, pressure is now rising, and it still behaves in this kind of bell curve manner. But what they find is, as you can see from the caption here, a shorter ignition delay leads to a lower rate of pressure rise. And what they mean by that is the pressure doesn't rise as steeply. The curve is not quite as steep. It's a little more flat. And what you can also see is that the maximum pressure occurs a little bit later, and it doesn't rise nearly as high. It doesn't rise to here, it rises to here. So there's a difference of about from here to here. Now, what does this all mean? I mean, you can see that there's a difference in how length of ignition delay affects what that pressure looks like. Well, basically what we can see from a practical standpoint is that a shorter ignition delay leading to a lower rate of pressure rise, what that does is it makes the engine run a little bit more quieter and more smoothly, because the pressure, the sharpness of the pressure rise on a longer ignition delay actually makes the engine run more roughly and does not let it run as efficiently as it could. So, enough of the graph. Let's talk about cetane number. Okay, now cetane number is the index expression of the combustibility of that fuel, as we mentioned before. How is it measured? Well, there are a couple of different ways you can measure cetane number, but the tried and true old school method to measure it is the ASTM D613 test, which is also called the CFR cetane engine method. And it uses a single cylinder, a special engine that has the ability to vary the compression ratio and it also has a hand wheel that's calibrated. And basically what they do is they take the test fuel, and then they also take two what they call bracketing reference fuels. Basically, it's one fuel that's very high cetane, and it's also, they know what that cetane number is. Let's say it has a cetane number of 150 or whatever, but it's a bracket fuel. In other words, it's a reference on a very high cetane number that we know what it is, and one that's very low on the other end. It might have a cetane number of, I don't know, 10. So they take readings for all three of these, and then once they've got that, then they're able to plug the readings into a formula, and they are able to calculate and come up with a cetane number for the specific fuel. Those two reference fuels we talked about, the high one is what they call normal cetane, or it's N-cetane. Normal is just a chemistry term. It's basically it's a cetane molecule, and we've been talking about cetane as this concept, and it is a concept, but it is also the name of an actual molecule, an actual kind of hydrocarbon. So they use N-cetane for the high bracket fuel, and they use this stuff called heptamethylnonane for the low. As you can see, N-cetane has an established cetane number of 100. Heptamethylnonane has an established cetane number of 15. So they take the results, they plug them into formula, they come up with a cetane number, and that's how you know what cetane rating your fuel is at. Okay, now we just mentioned cetane number, but it's also useful to mention this thing called cetane index, because sometimes what you will find is that those figures are used maybe interchangeably in place of each other. And what we have to realize, if we're going to be really accurate about this kind of thing, is that cetane index is actually different from cetane number, or at the least it's calculated different. First bullet says that cetane index, it's a cetane number calculation. Okay, it's not based on testing the fuel in the same manner that we just described when we were talking about cetane number. What it is based on is they take some other measurements of the fuel that are produced by other tests, and they use them to estimate what the cetane number of the fuel is, without having to go through the time and expense of putting it into a cetane engine and coming up with the actual measured number. So it is basically an indexed estimation. It's based on the gravity or the density of the fuel. It's also based on the recovery temperatures of a distillation test. So they can take those two figures and they can calculate, predict what the cetane number is likely to be. But because they didn't actually measure it in a cetane engine, they won't call it a cetane number, they'll call it a cetane index. Now, important distinction that from the standpoint of someone that might use cetane improvers, it's important to recognize that a cetane index calculation does not actually account for the presence of a cetane improver. So you could take a fuel, let's say you take a fuel that has a cetane, actual cetane number of 40. They measured it on a cetane number engine. And let's say they took that same fuel and they did a cetane index test, and it also came out as 40. Okay, so far so good. But then they took and they added some cetane improver, and they got the actual number of the fuel up to 45. And they know this because maybe they tested it on a cetane engine. If you were to do a cetane index test on that treated fuel, it would not show 45. It might not show 40, but it's not going to show 45. And so for the purposes of trying to know the correct properties of the fuel, you would never use cetane index in order to measure change in cetane number with the addition of a cetane improver. The actual number of the name of the test for cetane index is D976, or there's a D4737 test as well. All right, so cetane improvers. What do they do? Well, cetane improvers We mentioned this when we were talking about that ignition delay. The basic thing that a cetane improver does when it's added to fuel is it reduces that ignition delay. It makes it shorter, or it reduces the time that passes between when the fuel is injected and when combustion actually starts. And of course, it's well known that if you want to increase the cetane number of diesel fuel, you can do it by a couple of different ways. You can use a cetane improver additive, or you can do it at the refinery by doing certain things like hydrogenation. Now, for our purposes, we are not a refinery, so we can't do the second option. But we do, as consumers and as fuel treaters, we do have the ability to positively impact cetane number by formulating and using effective cetane improvement treatments. Typically, there are two main things out in the chemistry world that are used to improve or raise cetane number. 2-ethylhexyl nitrate is the most common one. It's also referred to as 2-EHN. It's probably the dominant one in the marketplace. There's also another one called ditertiary butyl peroxide, but it is not used nearly as much as 2-EHN. Now, the reason we mention this is because there's only, just like with octane improvers, there's only a few things, there's only a limited number of choices you have when you determine that you need to find something to add to the fuel to increase cetane number. So when we say that a cetane improver is made up of a certain percentage of 2-EHN, it's not like it's a government secret that we're divulging here. People within industry know these things pretty well. It's kind of very much an open secret out in the industry that those are really the only viable, feasible options that you have if you're trying to accomplish this, to raise cetane number. So cetane improvers can function as both a marketing and an environmental additive. Okay, environmental additive, what we mean by that is that when someone is asking, what value does a cetane improver have for me? Well, you would couch the answer to that in terms of, well, it's going to do this for you, and it's also going to do this for the environment, which also has benefits for you. So from an environmental standpoint, it does things that make your diesel engine setup better for the environment, and it also does things that improve the bottom line for a business or a fleet that's having to employ it in their fuel. So what kind of improvement can you get when you add a cetane improver? Now, Bell Performance's cetane improver is branded as Super-Tane. It is a 2-EHN formulation, and what you have here is you have 3 fuel samples of these are low sulfur diesel samples, and you have A, you have B, and you have C. Now, the base for these, one was 45 or 44.5, the other one was 43, the other one was 41.3. Now, keep in mind that the minimum cetane number that you are allowed to have in the United States for legal on-road diesel is 40. Also keep in mind that when you go to other parts of the world, it's probably going to be higher. I know that it's higher in Japan. It's also higher in the European Union. It may also be higher in places like California, depending on when you're listening to this. But these 3 samples, 44, 43, and 41, and you add varying amounts of cetane improver. In sample A, you added 500 parts per million. Part per million is a simple mathematical base that basically means 5/100%. Probably you could figure out a 1-to-X treat rate by simply taking 1 million and dividing it by 500. I believe that would come out to 1 to 2,000. So it's a 1 to 2,000. That means for every gallon of low sulfur diesel fuel A, they're adding 1 gallon of Super-Tane cetane improver. So they treated each of them with 500 parts per million, and what they got was they got a 4-point improvement here. They got a 3-point improvement in this one, and they got a 3.7, almost 4-point here. Then they also took similar samples, treated them with 1,000 parts per million. Now, they didn't do it for A, they did do it for B, and what they found is they got about an extra 2 points. So by using 1 to 1,000 ratio of cetane improver, they took a 43 cetane fuel and they made it almost a 48. And there's going to be a substantial difference in how it's noticed to be performing between, if you're comparing a 43 to a 48. They also got here, they turned a 41 into a 46 and a half. Again, substantial difference. Now, they also took this fuel and they said, well, let's add 1,500 parts per million. And so they got an extra 1.5. They got it all the way up to 48. So the takeaway from this slide is that you don't need that much cetane improver in order to substantially raise the cetane number of that fuel. This is another graph. This is a different kind of graph that shows the differences in response for aggregate numbers of diesel fuel samples. And the reason we talk about aggregates here is because, you know, when you ask a question, how much, if I use Super-Tane, how much is it going to increase my cetane? Well, you're asking someone to make a predictive judgment. And there are certain things that you can know, and there's also certain things that you can't know. And in the absence of having a specific fuel sample of your specific fuel or of their specific fuel, and then treating it with a known quantity of cetane improver, and then measuring the number before and after, you cannot have an exact definitive answer. Unfortunately, that's what a lot of people want. And so what we're left with is having to make predictions on what's likely to happen. And in order to do that, we use graphs like this. We say, okay, we have concentration of cetane improver here, 0, 250 parts per million, that's 1 to 4,000. 500, which is 1 to 2,000, up to 1,000, and then up to 2,000. 2,000 ppm is about a 1 to 500. And then you have change in cetane number. And what you see, of course, is that the more cetane improver you use, the higher the response. Now, another couple of things you should notice here are it's not a linear response, as in it goes in a straight line from here, straight line to here, such that 1,500 parts per million is twice as good of a response as 750. It doesn't quite work that way. What you find is the same thing that you find when you're looking at cold flow improvers relative to CFPP temperature. What you find is that the effect is greater in the beginning, but the more you add, it still rises, but the rate of rise tends to level out, and so you get a curve that looks like those. The other thing that you should notice is that there are good response fuels, average, and poor response fuels, and that's where the whole predictive problem comes in, because short of actually testing a specific fuel sample, you don't know exactly if it's going to respond poorly or if it's going to respond well. Now, if you take a step back and you look at cetane improvers out in the marketplace, a lot of them will, or not just single function, but multifunction products that make claims that they will increase cetane. Many times you will see, increases cetane by 6 to 8 points. Now, what they really mean in most cases is that if you add enough of this, it's possible that that could happen. Unfortunately, that's rarely true at the base treat rate that they state, because they want to give themselves a competitive advantage over all of those other additives that are making the same claims. And so what they do is they say, well, you only have to use 1 to 1,000 of this, and if you use 1 to 1,000 of that given one, you might get a 1-point increase. But that's not very impressive when you talk about marketing claims. So they say, well, it'll increase it by 6 to 8 points. And if they were, being legally held their feet to the fire, they would probably have to have a little asterisk there that says, we'll increase cetane 6 to 8 points if you use 5 times the treat ratio or whatever. And then, of course, suddenly it doesn't look nearly as attractive to the buyer. So you can see that there are poor response fuels, average, and good. And so let's just look at the 1,000 ppm of 1 to 1,000. What you can see, the takeaways you can see, is that in some fuels, it will increase it by, let's say, up to 3 points. It could be anywhere from 0 to 3 points. What you can also say is that, yeah, but the average response wasn't 0 to 3. It was actually more like 3 to, we'll say about 5. So average is 3 to 5. And then you could also say, but there were certain fuels that responded well to cetane improvers, and those ones actually got from 5 to 7. And so if you're being correct about this, what you could say is that 1,000 ppm of cetane improver, very likely it could increase your fuel up to 7 points. Now, it doesn't necessarily mean that it will increase it by 7 points in every kind of fuel, but there's enough testing evidence to show that that's within the range that you could possibly claim. Now, why and when would you use a cetane number improver? That's what CNI is, cetane number improver. Why would you use it? Well, if you were an additive formulator like Bell Performance is, you would add it to a diesel package in order to increase its value. And that's exactly what Bell Performance did. Back in probably about 2013, we reformulated our base diesel multifunction and added cetane number improver to that, and to make it a more valuable product that added more value to the consumer. You would use it, again, as an additive formulator. You would use it to differentiate the product. I mean, diesel is now differentiated from any number of other multifunction diesel treatments because it actually does have cetane improver in it. You could use it as part of a value-added program. You could use it to help meet emissions goals, and that's especially true for users in whether it's fleets in urban areas, which always have issues with urban air quality and running afoul of the EPA limits. It's also especially important for places like underground mines. An underground mine is obviously an enclosed space, and you can't have excessive carbon monoxide and excessive emissions fouling up the air in that place. So there are strict air quality controls, and many times a mining company can use a cetane number improver to help meet those goals simply by treating their fuel. And of course, refineries, those last 2 points relate specifically to refineries. A refinery will sometimes use a cetane number improver when they're blending their diesel to help them meet the legal goals that they have to meet in terms of the specifications of the fuel that they are producing. Okay, what performance benefits, performance effects does increasing the cetane number have for the end user? If you are an end user, this is the part that is specifically relevant to you. What benefits are you going to see if you use a higher cetane fuel, or if you take a low cetane fuel and you add Super-Tane to it? Well, you're going to see one or more of all of those things that you see on the screen. It's going to be easier to start in cold weather. Now, they have redesigned diesel engines so that they have things that make them easier to start, but in principle, a diesel fuel that's a higher cetane number will ignite faster, and it will cause the engine to be easier to start in cold weather. You can reduce fuel consumption. Now, fuel consumption claims are always tricky because there are lots of things that go into fuel consumption. They're tricky also because that's the thing that people care the most about, and so there are plenty of companies that formulate worthless additives that tell people just what they want to hear. So they'll make mileage claims that are way, way out of reasonable league, so to speak. So they'll say, well, you get 15% or 20%. You would never want to claim that for a cetane improver. Cetane improver will improve fuel consumption by up to 4%, somewhere in that range. Now, that's certainly not chump change, especially for a B2B user, like a fleet that goes through tens of thousands of gallons of fuel a week or a day or whatever. For those kind of entities, even 1%, 1.5%, 2%, can represent big savings. So reduce fuel consumption, definitely reduce exhaust emissions. The typical exhaust emissions are hydrocarbons, that's what HC is, carbon monoxide, which is CO, and NOx emissions, NOx. Notice that we do not have SOx, SOx emissions, because cetane improvers don't reasonably impact sulfur oxide emissions, because those are really controlled by removing the sulfur at the refinery level. You'll get less white smoke, which white smoke is indicative of unburned fuel. It's some of those particulate emissions. So the fuel burns better, you get less unburned fuel, you get less white smoke. The engine warms up faster. It has reduced noise, and what that means practically is that it sounds like it's running smoother, it's running quieter. And then, of course, improved engine durability. So all of those things are reasonable claims that you can make for a cetane improver. Now, how much of a benefit are those? What's the benefit level? Well, let's look at a few graphs here. This is a graph where they took a number of different samples of diesel fuel. Some had cetane number improver in there, some did not, and they had varying cetane levels. Cetane numbers graphed on the x-axis, and then what they did is they graphed the number of emissions, the amount of emissions. In this case, HC means unburned hydrocarbons, and they're measured in units of grams per brake horsepower per hour. Okay, so that helps them account for an engine that's running at a higher horsepower. That's used to help control those kind of variances. So what you find is that, remember, 40 is the kind of the legal starting point. Well, they have a couple of fuel samples that are below 40, so these are really bad. And you can tell that they're bad in part because they produced pretty high levels, above 1 gram per bhp. So you have like 1.1 and almost 1.2. They took some cetane number improver and they added it to those, and they got the cetane number up to 40, and they were able to reduce the emissions substantially by about 20%, from about 1.1 here down to almost 0.8, maybe 0.85. Another couple of other samples here. You have a sample that's about 43, let's say, another one that's 44, and those are burning at about 0.6 grams per bhp. Another couple here, 3 fuel samples that are around 49, and those are, producing about 0.3. The trend that you can see here is that as you get a higher cetane number, the emissions go down. And so in accordance with that, they treated some of these fuel samples, got the cetane numbers up to 49, 50, and then up here, way up here, like 55, and you can see that the number of the amount of emissions has actually stabilized. There's not much difference in lower hydrocarbon emissions between a 55 and a 49. And so what that also tells us is that, again, it's not a linear relationship. It's not a linear benefit. There's a substantial benefit between running a 40 and a 44, but there's not that much of a substantial difference between a 48 and a 56. And so if we're talking to our customers and we're saying, we're giving advice on what they should do, one of the things that Bell Performance really strives to do is to always keep our customers' best interests in mind. And so we would never tell them, well, you're running a 49, and your engine only needs a 44, but you should really add cetane improver and make it a 55, because that's not really going to benefit them that much. And in the end, we've been around for 100 plus years, 2016, and now makes it 107 years. We've learned that people appreciate when you keep their best interests in mind, and they definitely don't like to feel being taken advantage of. Okay, what about carbon monoxide emissions? Carbon monoxide emissions are really, really bad, because carbon monoxide, of course, we know that you breathe enough of it, it'll kill you, and it's a substantial component of poor urban air pollution, basically. And so what you can see a similar kind of curve here. You can, again, see cetane number graphed on the bottom, and then carbon monoxide emissions expressed in terms of grams per brake horsepower on the y-axis. You can see somebody running a 40 was emitting 2.6 grams. Somebody running a 46 was emitting 1.8. That's a substantial difference. Somebody running a 48 was running about a 1.6. Somebody running a 50 was down to 1.4. And so you can see from this graph that raising the cetane number of the fuel lowers the carbon monoxide emissions production of that fuel in a linear manner like this. Okay, what about NOx emissions? NOx emissions are very much the same thing. Again, in fact, the data looks almost identical. So the takeaway here is that for hydrocarbons, carbon monoxide, for NOx, and then also for particulates, the higher cetane you go, the lower harmful emissions you will emit. Particulate matter, which is the black sooty smoke that you see, particulate matter is really the only one of those major emissions that behaves in a linear fashion. Here, it's a straight line. Somebody running a 40 is going to be around, 0.28, and it's grams per kilowatt hour is how this is measured. If you run a 48, you're going to get it down to about a 0.25. That's probably about, I want to say it's about a 15% decrease. White smoke. White smoke is usually measured with an optical reader, like a Sebolt reader. So they measure white smoke in terms of a percentage, and then they also measure it relative to cetane number. And what you can see is that if you're running a 46, which is still pretty good quality, you're at about a 65. And then as you get to 50, well, at 50 you're at almost half, and then the curve kind of flattens out around here, or about down here. What about noise reduction? It's been claimed that running a higher cetane fuel will make the engine run quieter, and the analytical evidence shows that that is true. They took two different kinds of engines: a high-speed engine running under high load, that's the red line, and then a medium-speed engine running on a lower load. And they measured the noise of operation in decibels. So they start with a 42, and for the medium-speed engine, it was pumping out maybe about 98 decibels, which is pretty loud. They increased the number to cetane number to 55. It goes down in a linear fashion, and they were able to knock off almost 3 decibels in noise. Now, the more impressive result was with the high-speed engine. The high-speed engine running under high load, 44 cetane, you're looking at probably about, we'll say, 107 decibels. That was actually reduced by 7.5 decibels down to under 100 if they were able to increase the cetane number by about 10 or 11 points. So the takeaway there is not only do cetane improvers markedly improve harmful emissions, but they also make the engine run quieter. All right, so from a refinery standpoint, most of you are not going to be fuel refiners, but if you were, you would know that the benefits that you would get, well, first benefit is that you would allow, it helps you better able to produce the type of fuel that you need to produce. You can take a low cetane diesel stock, and you can blend other components, like let's say, it says like a light cycle oil. You have more options in terms of what you're blending into that, because you know that you can add cetane improvers to get the final product up to where it has to be. And you can do it in a more economical fashion than simply chemical hydro treating like some refiners have to do. And it also enables you to better weather what they call refinery upsets, because refineries do close down. Refineries do have equipment problems. They have things that cause them not to be able to produce every kind of fuel all the time. And having a cetane number prover it's basically an essential element of the refiner's portfolio that they will use to produce what they need to produce. Okay, some important final facts about cetane number improvers. Okay, you saw this earlier, but it's worth mentioning again. The difference in response for fuels, there's variance in response. We would say fuels vary in response to cetane number improvers. You saw that when we were showing the range of possible improvement between low response, average response, and good response fuels. And again, the only way to know for sure how a fuel is going to respond to a given percentage of cetane number improver is to actually put that in a sample of said fuel and run a cetane number test, not a cetane index test, but a cetane number test. Excessive amounts of cetane improvers can affect thermal stability and can affect lubricity levels. How much they can affect, we can't say at this point, but luckily there are options that can be used concurrently with cetane improvers that will help buffer that degradation. So there's thermal stability improvers like Diesel Life that can do that, and there are lubricity treatments like Lupro and even low levels of biodiesel that can help blunt that effect. And then the last point there, the EMA, the Engine Manufacturers Association, has for a while been arguing that the minimum cetane number should increase from 40 to 42. Other parts of the world, as we said earlier, other parts of the world have already increased it. Japan, I believe, is 45, and there are parts of Europe, I believe, that are moving towards 50. And typically, when that happens in those parts of the world, then typically California in the United States will move towards that, and then eventually we will see the base ASTM D975 diesel fuel spec, we will see them fall in line with that. All right, so that has been our training today on cetane number improvers and their effects in fuel. Again, my name is Eric Bjornstedt. I'm Technical Information Director at Bell. If you have any questions, you can call us at the office. Also visit the Bell website at bellperformance.com. We have a lot of good information. We also have a couple of blogs. We have a consumer blog, and just as importantly, we have a B2B blog, which deals with fuel issues, talks about fuel issues that businesses and fleets and municipalities and emergency management people like that, things that they're concerned with. So encourage you to check it out. Just go to bellperformance.com. So thanks for joining me today, and we'll see you next time. Bye-bye.